All right, so here we are at the chain rule. So believe me, this rule is another universal rule and you will never escape from it. So starting from this point on, once you learn and realize its existence right here, then anywhere you go, I challenge you. You go to Cal 2, you go to Cal 3, you go to differential equation, you go to any other class, as long as you are doing the derivative there. At that class, there will be the chain rule being involved there. And for the rest of the quarter, be aware that there will be a lot of instances, many instances where the chain rule that we're learning today apply again. Okay, so I am going to erase the title here because I need to take a lot of more space to write. And instead of getting directly into what the chain rule is, I'm going to start out again by introducing a couple of problems that promote the idea here. Okay. So the first problem to promote, and of course, even though I'm talking about, we're learning about the chain rule, but let's not be worried about what the chain rule is at this point yet. So at this point, anyone arriving at this video lesson of mine has viewed and learned a lot of rules in terms of how to find the derivative. So let's find derivative again. The entire purpose of this course in Calculus 1 is all about finding derivative. So I am going to bring up a problem as following. So we are given, okay, a function expressed in expressed in the equation form. So y equals x squared plus 4x, but then in parentheses. So the expression x squared plus 4x being in parentheses and being raised to a square power. Okay, so and I need to correct my writing here a little bit. Okay, so x squared plus 4x in parentheses square. And of course, for a problem like this, we are asked to find dy dx. We want to take the derivative or differentiate this function y in respect to x, meaning treating x as the main variable of this function. So up to this point, the only rule we have learned is, the only rules we have learned are the basic rules, the rule on constant coefficient, the rule for taking derivative of a constant, the rule for taking the derivative of a sum, the rule for taking derivative of a difference, the product rule, and a quotient rule. Okay, and further we can find and we learn a rule specifically for the power family, the power rule. But that's about all. So those rules we have learned are just enough to solve a problem like this one. So before I even find dy dx, so notice how my x squared plus 4x is being inside a square power. And so a good start would be, I am going to rewrite my expression here as x squared plus 4x times x squared plus 4x. And believe me, anyone viewing this video must have seen how this work has been done all over throughout my past lecture videos. So I'm just simply putting the square here as a product of two identical factors. So somebody at this point can use the product rule to apply directly to find the derivative. That's one way. I am not going to use, in this video lecture here, I am not going to use a product rule, even though it's all gonna arrive at the same answer. What I'm gonna be using is just the standard FOIL. So I am going to be foiling out my term by terms right here. So my y function, and this is still again before finding derivative. So my y here is after foiling and combining like terms, I'm looking at y to the fourth plus 8. I mean x to the fourth plus x plus 8x cubed plus 16 x squared. The reason I went for foiling because I just want to lay down the function here all in three separate terms, term by term, so I can easily apply the power rule. It's just my favorite choice right there. But if anyone would like to go for the route using the product rule, you're more than welcome for doing that. And then at this point, I can easily apply the power rule on each of our terms here, and with a little bit of the other rules. So now I'm ready for my derivative here. So dy dx is going to be, first term is giving me and at this point, hopefully anyone viewing my video is fluent enough with all the basic rules. So I am going to start picking up pace a little bit here, but 4x to the fourth, x to the fourth from the previous step now is going to give me 4x cubed as the derivative. So this is the derivative for x to the fourth from the previous step. Now I'm going to add according to the sum rule, and now my middle term becomes 24x squared, because what I did here, I multiplied the initial power, the beginning power. The beginning power was 3, and I multiplied down the power and multiplied together with that constant coefficient, and the power being reduced by 1. And so in that way, that's how I got my 24x squared, and the last term here, of course, becomes 32x squared, as once again the 16 was a constant coefficient from the previous term, from the last term of the previous step, and then the power after taking the derivative is multiplied down into the front, and together with that 16, that's how I ended up with 32, and the power in our derivative here is a power 1. So we have had our derivative, which is just fine. So nothing big about this problem. We can find the derivative easily by simply re-expressing my square right here as a product of two identical factors, and we're going to start taking the FOILing, or from here anyone can go with the product rule route. Okay, and what I mean route here, so anyone can at this point can be flexible enough that one problem we can go with so many different routes to get to the same answer. So this problem is easy. But so now let me bring up another problem. The FOILing seems to be getting the work done, and nobody at this point viewing my video is going to feel like there's a need for a new rule to learn. But now, how it feels easy about this problem stops when I simply switch this problem. So now I quickly introduce another problem. So the same problem, we have an x squared plus 4x, but now in parentheses, how about I'm going to raise to the fifth? Okay. So I wrote that fifth power in red ink to catch everybody's attention. So it's pretty much similar to the earlier work, but now we have a much higher power. So let's find the derivative again. Think about that for a moment. Yes, we can re-express that fifth power of the x squared plus 4x as, so there's a factor x squared plus 4x. I'm going to multiply with another x squared plus 4x, and allow me to write small. And I'm going to multiply with another x squared plus 4x. And I'm going to multiply with another x squared plus 4x. And I'm going to multiply with another x squared plus 4x. And I keep multiplying until I reach enough, displaying enough as a product of five identical factors. And now at this point, it's going to be a good luck wish to anyone trying to FOIL. I don't want to FOIL something like this. I mean, FOIL here have to take, FOILing out for the first two and FOILing out again. So for a problem like this, of course, sure, FOILing is still going to work. You got my word for that. FOILing is still going to work, but we definitely don't want to FOIL out something like this. Okay? And so the point now is that, is there a way to find derivative with no FOILing? Okay? And even product rule. Think about product rule. We have to take product rule of the first two. I mean, it's a very lengthy product. So taking a product on 5 factors like this is also challenging, quite challenging. No FOILing. Okay? And the product rule is not too efficient as well. Or actually I should have said it's not too useful. Okay, it's not very useful to use the product rule as well. Okay, gotta correct my terminology for that. So product rule is not that useful either. So I'm gonna put a pause right here for this problem, for this particular problem. It's just saying that the method with our limited understanding, all the methods we've learned so far based on our limited understanding, is not doing a good job for us. I'm not saying that we can't. It's just all of the methods we've learned are not doing a good job for us in this problem. So what about another problem? And I still have not delivered the answer or the solution to this problem yet, but let's put a pause on this problem right here. So what about, I am going to introduce another problem. So we're still going to have a function given, and here inside of my function I'm going to have a, how about in my function, x cubed minus 4x squared plus 5x plus 1. Okay, and now this time I'm only going to do a low power, a small power 2 right here. But, well, again, two choices of work at our up to our learning at this point. We can reproduce as one factor x cubed minus 4x squared plus 5x plus 1 and multiply. So basically the square here can be re-expressed as two identical factor x cubed minus x squared plus 5x plus 1 times another identically the same one like that. So x cubed minus 4x squared plus 5x plus 1. Two identical factors. But foiling is again quite challenging because each factor itself here is quite lengthy. And so product rule might help. Product rule might be a good idea. Okay. Okay. So product rule might be good, but still it doesn't convince me too much in terms of the efficiency of the work. Okay. Because you're going to have to remember the product rule say if you think of that as an f and this is a g, then we have to take the f prime, which is, you know, not that much shorter, and then multiply with g without prime, and then add f and multiply with g prime and more stuff to clean up the terms and all that. So product rule might be good, might be, I shouldn't say good, might be just okay. All right. So product rule might be just okay, but as in a sense that we can still do it. And foiling here also work, but we want to stay away from those methods right here. For this particular problem, we want to find something a lot more direct. Okay, so immediately after the very first promoting example, the very first introductory example, then I brought up two other examples here, and they both, I both have to, I had to put a pause on both of these problems here. I didn't deliver, you know, a solution to that because I want to save, you know, these for, you know, the later one when, you know, we learn a good method for that. Okay, so now no more beating around the bush. Let's go back to that very early function, the function that I brought up right in the beginning, and let's give it a second look. Okay, so I'm going to say, we're going to get back to our earlier one. Just that x squared plus 4x being inside. And now start noticing how many times I use that word inside. So what I have here is an expression x squared plus 4x and being inside a power 2 right here. And let's stay with power 2, okay, for, you know, being simple. So here's the thing. Let's have a moment to observe this. So, like as I start saying this oftenly enough, then people are going to start having a sense about we having a function x squared plus 4x, but being in a pair of parentheses then square. And so, or another way of saying that kind of informally, but we're looking at x squared plus 4x being inside of the square operation. Okay? So, once we're looking at that in that way, then think about it. Now I'm going to put this aside for now still. I'm going to put this aside. Let me create another problem here. Quickly, if we had a function y equals u squared, for now, just like I said, kind of forget about this problem for now. Okay, if we had a function y equals u squared, so the big U, the big capital U is the variable, okay, and so y equals u squared, then taking this derivative, see, take the derivative of u squared. It's simple, right? Anyone seeing this, take the derivative of u squared. It's simple by the power rule saying that we're gonna take that derivative and become and make it become 2u. All right, fair enough. So if u squared, if we take derivative of u squared, we can simply give 2u right here. Then think about this. If we back to this problem now, if we just simply let u equal x squared plus 4x, then if we're letting u, or we're making a little substitution like this, a big letter u to equal x squared plus 4x, then all of a sudden this expression will become the expression that we've had. So y equals x squared plus 4x all squared here will turn into, that's what my double arrow is indicating, is turn into the expression the y equals u squared. Okay, so that's just to open up your understanding. So if we can think of, and as my point I'm trying to make now is that if we can think of this u is to be in place of that x squared, of the entire x squared plus 4x, then my student in my past quarter, okay, so if we can do, my student in my past quarter already rang a bell for me. When classes were still face-to-face, my student said, if we can do this, u squared, take the prime and to equal 2u, then why not? Okay, and it was their question. And why not doing simply x squared plus 4x squared, take that derivative to simply give us, see, the power rule. The power rule here, see, instead of being the u, now we have an x squared plus 4x, but basically we have a power right here. Okay, it's a comma here, and take the prime here, then why not just u2 times x squared plus 4x. We treat all that x squared plus 4x as one variable u. That's one variable u. And then we apply just simply the power rule on that. Excellent thoughts. I mean, I'm not making judge about right or wrong yet, but it's starting an idea here that we can see some expression being inside another variable right there. Some expression being inside another variable. So I back at the time when classes or were still face-to-face, I had to say to the student, you got more than half of the problem done already. But unfortunately, this is not the answer yet. So 2 times x squared plus 4x in parentheses is simply not the answer to that derivative yet. But see, before I make that connection, before I point out how this is not the correct answer to our derivative of this function yet, let me get back to discussing about the students who talked to me, who told me about if we can do u squared prime to equal 2u, then why can't we easily do the derivative of this square, all power square here is being thus. His plan was to, let me quickly switch to the other board right here. The plan of that former student of mine was to apply exactly the same rule of x squared plus 4x. If what we'd done there was successful, if it was an allowed operation to find derivative, then he could have done that on the fifth derivative. And so this work right here could be similarly 5 times the entire x squared plus 4x being kept the same, but now simply to the fourth. Okay, that was their plan. You got to understand, from a student who are learning, then that was a really good the progress already. But sadly, that wasn't there yet. You see what I'm saying now? So let me point out why. So back to this problem here. So the reason I was saying that this is not quite our actual derivative yet, because recall for yourself, I actually worked out this actual derivative. Its derivative here was, so we had dy dx here was being, what was it? It was 4x cubed plus 24x x squared and plus, and this what the last one was a 32x. Okay, and so if we believed that we found a different way to find the derivative, then in the end, if we distribute out this common factor 2, we should arrive at the exact same answers. But obviously, this was the answer we found using a different method. And after distributing out this common factor 2 over here, things do not agree. The two answers do not agree. Okay, so let me put it on the board here. All right, so 2 times x squared plus 4x. If we're distributing this, we're looking at 2. We're looking at only 2x squared plus 8x. But the actual answer we already found is y dx equals okay, dy dx was to equals 4x cubed plus 24x squared plus 32x. We're still quite far away from the actual answer. So what is going on here? So as I said, having that observation was a fabulous idea. This is where, being the instructor, I need to start adding on top of that some more ideas. But this idea is perfectly okay. It's perfectly good. We just need to add in some more the understanding so that we can complete the actual understanding. Okay, and so here's my explanation of why it's not working yet. Okay, so back to this. So we already observed that if the function was simply a u squared, which is, gosh, so much like this one. Okay, if the function was simply the u squared, so much like that one. And so I did also talk about a little bit about, or maybe let me completely erase this, and if we're having a direct look at this beginning problem right here, then here we can say, think about if we formally let u equals x squared plus 4x. And the work there, think about it, the idea here was that, now I'm saying the term that we're substituting, but sometimes people can just simply think that this expression x squared plus 4x is going inside of the u variable. So now substituting x squared plus 4x to be a new variable u right here, then of course the expression here becomes y equals a big U squared. But see, this is how I'm saying that the expression y equals U squared, but it already has, this expression, this equation has the expression x squared plus 4x as the inside. Okay. As the inside of the variable u right there, being the inside of the variable u, or a little more, for anyone who is more comfortable with algebra, who is a lot more comfortable with algebra, you can just directly look at that and see all that. Think about, we can just hide away this expression right here, then the entire square is playing in the place of that u. So u square is, the u is the empty parentheses here, but square. So we have that expression x squared plus 4x being substituted as the inside of that u right there. Okay, and so if that expression here is being the inside, then once we made a substitution, then just the u squared itself, right? Once we from that starting problem again, but once we now classify the x squared plus 4x as the inside, then now the u squared, after we substituted away the inside part, then now the u squared is the outside. Okay, the outside expression. Okay, so there's the concept of the inside and the outside expression, or all together. See, all that y equals u squared. The big U squared is being regarded as the outside expression. Or another way of thinking it. Let me get into the other board right here. Okay. So I talked along with just that idea. I'm talking about inside and outside. Let's look at that function again. And I'm still just beating around the bush. I'm still explaining the algebra of the function, but I have not done any derivative yet. So x squared plus 4x being inside the square. You see, here we can think of that. The inside I was trying to point out earlier, the x squared plus 4x as the inside. So usually many professors, including me, also come to this habit that just clearly lists down the inside. See, we saw there's the inside here. And so instead of like making a substitution, I can just call regard to this for x squared plus 4x. I can just simply regard to that as, instead of calling that u, I can call that some function g of x. Okay? And then the outside function, along with what we picked up from the earlier explanation, then the outside, there's a different way of understanding that here is that we can have a function x squared. Now this x is not necessarily the same with that x right here, but it's just a variable of some function. And I call this x squared function the f of x function being the x squared. Okay? But now the concept of inside and outside is that because if we put now, and so people who came to this class must have done some algebra, some pre-calculus, and in your pre-calculus course, this idea was introduced all over. But we're putting g inside. This is the composition of f and g right here. We are putting the function g to substitute for the expression for the x variable in our function f, and that's why. In this way, what we recognize now is that our function, the x squared, is here. Our outside function is the x squared function, but now x is empty, being ready to be substituted by the inside expression, which is now x squared plus 4x. So all together, we're looking at x squared plus 4x in parentheses all squared, and that's the anatomy, the algebraic structure of our beginning function y equals x squared plus 4x. Okay, so now, and of course, I try my best to give all the explanation about the inside and outside, and after we later do a few examples on how we apply the new derivative here, I am going to do another short discussion on how we can successfully recognize the inside and an outside, because right now it might be quite easy for anyone, for a lot of people, but trust me, it will starting to become more challenging when it comes to recognize the inside and the outside function. Okay, so two different ways. You can think of that entire problem here as, here's our function g, the inside function x squared plus 4x, and then the entire expression here is truly our function g being inside of the standard squaring function. Okay, or like how I explained earlier, then we can think of that. We can substitute away that expression inside of the square. And then so now that's why I'm seeing x squared plus 4x as the inside, as an inside expression of the variable u, because it's substitute for u. Okay, but once we substitute away this by the u variable, then we would remain the u squared expression, and so we can regard to that as the outside expression. Okay, so at this point you're probably starting to feel, Mr. Dung, I'm so impatient. Let's get into the derivative, because so far I'm just talking about the algebraic structure of this function. So much beating around the bush, but now you're ready. Okay, so immediately from here, but let me clean up and make more space for myself here. All right, so for that function, once again, we already kind of thought about if we're letting u, we substitute u for the entire expression x squared plus 4x because we regard to this as the inside right here, then of course, like I explained earlier, our entire function becomes y equals u squared. Okay, but see, if we're doing this, well, if our derivative initially thought to be just simply brought down to 2, because see, the derivative of u squared, is simply 2u. So a lot of people is going to start implying that, hey, since that way and inside of u was that expression x squared plus 4x, then why not simply just regard to this 2 times x squared plus 4x being the final derivative of this. But see, here's how it happens. This 2u right here, and once we substituted away the entire expression x squared plus 4x to be a new variable and arrive at this one, it's all good. We arrive at this one. But now I have to make a note for you, for everyone, that this right here is not our dy dx. Remember, our goal here is to find dy dx. Have a good look at that symbol over here. So y is a function. But the dx, in some of my discussion earlier, in some of my lecture earlier, I discussed about this symbol, hopefully formally enough, that the dx in the denominator indicating that we're treating x as our main variable. But the way how it looks currently up to this point is not the dy dx. This is actually dy, but over du. Because we're entirely treating, because once we made that substitution, that's where another problem came along the way. The problem now is that we completely change our problem to a new variable. So this derivative is all good, but it's the derivative in terms of the new variable, the variable u. So even if we're using this right here, even though if we're rewriting with that involves the x squared plus 4x in there, but in the end this is still not dy dx. This is dy over du, because all that here is still being thought of as the u variable. You see what I'm saying now? All right, so but we're getting there. So now the rule I'm about to introduce, say, okay, the rule I'm about to introduce, now say the actual dy dx. To find the actual dy dx there, we just from what we already had initially as the thought right here, 2 times x squared plus 4x, but again, in my explanation so far, this is only dy du. Okay, this is not our dy dx yet. And the rule I'm about to say now is say that all you have to do is simply multiply your current thoughts. See, I didn't take this as my thought. I want you to understand that students can come to this close already. The only missing thing that I need to fill in for them is now as a product. This current thought that many of my students gave me, all they do now is simply to multiply with, see, think about like this. If I'm just kind of branching out into a separate work right here a little bit, but if u is defined as x squared plus 4x, have a moment to think for me. What do you think? Du dx, because now if u is an x squared plus 4x, and sure, u is a function of x. Don't you agree with me? Then so I can legally find a du dx. Have a minute, quickly find that du dx for me. All right, so hopefully you're back with your own du dx. So du dx, right from this substitution we made, is 2x plus 4. But this is the du dx. So now with that little piece of work right here, now I'm telling you what you need to do here to really find dy dx. You're going to take your dy du that you already had previously as the initial thought, just simply directly multiply, apply the power down. Okay, but now I'm going to multiply with that 2x plus 4. Whoa, so wait a minute, what was that? Where did that come from? This is the du dx that I just briefly talked about. So this is the du dx that I'm talking about. Okay, so ladies and gentlemen, the rule we are about to learn is stating as follows. Okay. You see, in our problem, we start out with y equals x squared plus 4x in parentheses, right? And then we made a substitution, and we let u equals the x squared plus 4x. So here I'm formulating the chain rule over here. We want to find dy dx because ultimately y is a function, an overall function that's in terms of x as the final variable. But along the work, we did a substitution by letting a new variable u to replace for the entire x squared plus 4x. And so with that, then see our equation quickly became y equals a u squared. Okay, so y equals a u squared, but in the meanwhile, the u inside of u, there was a u equals x squared plus 4x. And so there's the out sign, there's the in sign. So now the final derivative dy dx that we were looking at, kind of summarizing all that work here, was simply found by we took a dy du, because that was what the 2 times x squared plus 4x is all about, and multiply that with du over dx. But that's what we found, and we refer to this as this is the famous chain rule. Okay. All right. So now, after trying to get a hang of what the chain rule is, so let me give it another look again. So in this board of mine, so the derivative we already found. Dy dx in our problem here was the 2x squared plus 4x, all in parentheses. And then we multiply with the extra, the 2x plus 4. Okay? And so earlier, just when I was still on the other board, I was referring to this as the dy du, and this is the du dx. Just fine. Yes, that's correct. But now to bring it a little closer and along with what I was explaining the whole time so far, this here, the dy du that's formally written in the formula. This is a lot of time many instructors, students, including me, is understood this as the derivative of the outside. This is the derivative of the outside function. That's a different way of understanding that. Instead of seeing that as the dx, as the dy du, somebody is not comfortable with that, then we can see that as the derivative of the outside function is the squaring function. So we take the derivative of just the squaring function, keeping all that expression inside the same for now. So that's the derivative of the outside function. And then we multiply with the derivative of, see, where did this come from? The 2x plus 4, that came from, this is, formally it's the du dx, right? But du dx, so this entire x squared plus 4, it came out from that substitution u equals x squared plus 4. So I recall again, this is the inside expression, and this is the derivative of the inside expression. So 2x plus 4 now is a lot of time in verbal term is being regarded as the derivative of the inside, the inside function. And that's another way to get a hang of the chain rule. Okay, so the chain rule says anytime that you're taking the derivative of any function where you recognize there's some function you can regard, some expression that you can regard as the inside, and then outside of that there's another operation, then you can just simply take the derivative of the outside, keeping all that expression inside the same, but then we are going to multiply with the derivative of the inside function like that. Okay, and still another way of saying the chain rule. So this is the chain rule in right, so this is dy dx, right, to find the final derivative, dy dx, in formal, in verbal terms right here. Okay, so along with this way right here, we talked about inside and outside function. So another way of seeing this, then with our function again being y, let me completely erase this, with our function in the beginning being y equals x squared plus 4x squared. So another way of seeing this is, see, back to the concept of tracking down the inside and the outside function. Then I also use the functional notation. So inside, you see, the truth is the truth. The inside is the inside. Once you recognize it, it's the inside. It's how we want to express that. Different professors, different students can express it differently. So instead of using a big variable u, here I can regard to all that as one function, g of x. Okay? And the outside function is a squaring function. So here I'm seeing that as f of x equals x squared. And so yes, your entire function x squared plus 4x in the square here is the same as we putting our function g being inside of f of x, or in other words, f is composed of g here. That's another way of how the algebra classes been using as a term, as a formal term. Okay, but so in that way right here, then here's how we found it. See, our answer was the final dy dx that we found was a 2, just like that, right? 2 times x squared plus 4x. Gosh, how many times have I repeated this, the final derivative? But so this is the derivative of the outside. And so, but in the understanding of the g and f being composed together right here, then what I see here is that this is the derivative of the function, the outside function, f prime. See, this too, because f itself is the square function, and so we just simply brought the square down and we're keeping the entire thing here the same. But the entire thing here that I'm pointing at, my fingertip is pointing at right here, is our g of x being kept inside. Okay, so this is f prime of g of x. And then what I did in my, what I showed in my earlier example was that after this derivative of the outside function, we have to multiply with the 2x plus 4, but 2x plus 4 here is the derivative of the inside function, and the inside function of ours right here is the x squared plus 4 function. So here this is the same as g prime of x. So this is another way of saying that when our function is in the form of f, but take g inside, okay, and we want to take the derivative, and taking the derivative of the entire function, then the chain rule says we find f prime of g multiply with g prime of x. Okay, equals the f prime of g and multiply with g prime of x. Two derivatives are being multiplied together. So that is the chain rule. Okay, the earlier version where I had dy dx equals to dy du times du dx is another way of understanding your derivative, where all your variables are being directly substituted in terms of equations and all that. But so now that's the chain rule that we've learned. Different ways of writing the chain rule. Or in verbal terms. Once again, we just take the derivative of whichever the function we recognized as the outside function and multiply with the derivative of what we recognize as the inside function. Okay, so I'm still not going to rush into any example. Let's look back at the one that I kind of promoted earlier. So give me a moment to erase the board here. So this fabulous idea that we have found now is extremely useful in a case like this. And keep in mind again, this is not a formal example yet. This is just, we just want to immediately apply our problem. So how about here, if we're looking at a given function being y equals, see that x squared plus 4x, the same function there, but now being inside of the fifth power. Okay, see, I pointed out this problem here as a promoting problem, but we definitely don't want to use the foiling word. 5 identical factors is seriously too much to handle. Okay, or using the product rule, you have to go with take the derivative of the product of 2 and then again as a product of the next one, adding on too long. Okay, so we don't want to get anywhere of that. So what I do here, a couple of different options here. I can see that the inside, okay, I can recognize that all that expression where I underline being inside of my fifth power right here. Okay, so we can write it as a new variable u equals x squared plus 4x. That's one way of writing that. Or we can write it as a g of x equals all that x squared plus 4x. Okay, different ways. You know, the same video lecture here, I'm trying to use as many different styles of how other instructors and many other students out there are doing. So someone can do the entire here, but basically it's all about we replacing the inside, we tackling down right at the inside expression and substituting that regarding that as a new function, or substituting that for a new variable. Okay. And so once we tackle down the inside expression, then we're going to move on to the outside. And the outside, once we recognize the inside and the surprisingly, and a lot of time I also recommend my students to start out with this quick substitution first. Because once we make the substitution, then let's put the substitution in. So once we substitute all that here by u, then all that's left behind. Notice no more x. Only the new expression is completely in terms of the new variable. That's what I call the outside expression. Okay, this is the outside expression. Or here I can see that it's a little harder to understand, but f of x here can be regarded as the x squared, not that x squared. It's because, see, think about my bad the whole time. My mind still thinking about the earlier problem, but this is supposedly x to the fifth. Okay, this is to the fifth. So x to the fifth. So the x to the fifth right here is simply because, see, think about the whole problem right here. If I just simply hide out all that x squared plus 4x here, then I'm still having something being something. Some value, some expression being to the fifth, something being to the fifth, whatever thing that is being to the fifth. Okay, and so in this way of breaking it down inside, outside correspondingly, then the way how we see this is the way how I see now is that the function here, the entire variable y that we're looking at is the function f, but taking g inside of that. Okay, and that's how we ended up with the x squared plus 4x to the fifth right here. Okay, and here we don't need to do the extra steps. Okay, all right, but now we are so ready, because so far it's just beating around the bush with the algebraic structure, but it's not only just beating around the bush to really find out. Okay, I use the term beating around the bush in case I'm slowing any viewers down, but now this step, once we understand clearly where the inside and where the outside is. Now, option 1, we can go, see, dy dx. And in this case, I prefer going with this because our expression is already in terms of as an equation. So dy dx is, according to the chain rule, the derivative of the outside, which is this thing. We tackle that down first. So we need to go with the dy du first, and then multiply with the du, the du dx. Okay, and so in that way, what I'm seeing now is that dy du, so it's 5. All that u here is regarded as the 4x, I mean the x squared plus 4x, and being raised to the 4th power. Okay, and we're multiplying that by 2x plus 4. Okay, so that's how we find the derivative, the dy dx. All right, and if we're going with the other route, if we stay with the other route for finding that derivative, then okay, y prime or dy dx is the same as taking an overall derivative right from this. Okay, and that derivative is, once again, the chain rule said, is a different version of the chain rule. So here's a different version, so we need f prime of g. So using this notation here is making it clear that when you take the derivative of, when you're taking the derivative of the outside, we're leaving the whole g by the way it looks, and multiply with g prime of x. So that means my final dy dx here is going to be, now saying it out loud, the derivative of the outside is the 5th function, to the 5th power. And so that means we have 5, but g of x filling in x squared plus 4x all to the 4th power. And now multiply with the derivative of g. G is here, taking the derivative. We're looking at 2x plus 4. Okay, and so doing it using the chain rule, then we have a way, and it's a lot shorter. See, if we really have to crank through all the foiling work, we will end up with some derivative as well, and spend some time factoring out. I mean, we're factoring and we will come back to this form here. Okay, but this is our final answer. All right, so let me get back on the other board and quickly look at this answer over here. So it's still here with us, and we found the derivative using the chain rule. So, but before we discovered the chain rule, the derivative was the dy dx for this function was, and when that was a power 2 here, the derivative for that there was a 4x cubed plus, and then 24x squared plus 32x. Okay, so let's find out if the two answers agree. So there's a 2x plus 4 here. Okay, so how about I want to make my dy dx from this form right here to look like the final dy dx we have had way back in our beginning of this lecture. So the work is simple. Well, we just, I'm going to leave the 2 here. That 2, I'm going to leave it there. But now I'm going to start, I'm going to put a pair of parentheses, and we can just simply do the foiling work here. So x squared times 2x give me 2x cubed plus, right? And then here we're looking at 4x squared, and now plus 8x squared, okay? And plus, now 4x times 4x is a 16. I mean 4x times 4 is a 16x right there. And now multiplying, distributing that 2 for each term. Okay? And of course, combining these two like terms, don't we get this as the final answer? And so now we know that the chain rule was right. It gave us the correct answer, even though we could have had the answer in the other way, but now using other methods or using the chain rule as the methods, either way, the truth is the truth. The final answer is the final answer. So we got to make sure that the two answers agree right here. But so now, legally speaking, I decide not to provide a proof in a video lesson like this, but there are plenty of textbooks out there on the market and over the web that deliver the proof of the chain rule. I highly recommend any serious calculus students to read the proof, But here I'm just getting directly into the practicality of the problem and how we apply the chain rule after we learn what the chain rule is all about. Okay? And pointing out that the chain rule is a much more effective method to find derivative in case we have problem that being, some function being inside a power like this. Okay? And so I owe everyone who's viewing this video another little problem, a little gift right here. Because we also had that lengthy one, how about x cubed, and I forgot what that is already. Minus 4x squared plus 5x plus 1. But this time we're only going with the power 2 right here. So all of that there is such a lengthy cubic function being inside of a square. Okay, so let's find dy dx. Okay, and so how I recognize that here, it's always a good idea to start out by recognizing the inside expression. Okay, and like I said, for now I'm bringing up problems that easy enough that anyone viewing the lesson already have in mind what a good inside function expression could be. So right here, well, naturally speaking or intuitively enough, it's inside the parentheses, right? Inside the parentheses and being raised to a power. But trust me, I will have another some later part of our video lecture here, so that I can point out some way to guarantee you choose a good inside function. So the inside expression, the inside function is all that x cubed minus 4x squared plus 5x plus 1. See, and at this point I'm going to start going a little skippy here. Somebody can regard to that as a new variable u. That's fine, go with that. Somebody can go with that as a function g of x. That's fine with me too. Just go with that. I don't even care writing that. I'm just pointing out, hey, this is my inside. Okay, and then my outside is that function, is all that squaring right there. Okay, and that's the outside function. And so that's why, so f of x for the outside function going to be the square, but the inside function now we can regard to that as a g of x. Okay, all of that. All right, so now the derivative can be, and I don't even need to write down the entire complete the chain rule here, but the chain rule says we take the derivative of the outside, but keep in mind the outside function. So it's 2 times, but we have the input arguments of the outside function, we have to keep g in it. So that means here it is 2 times in parentheses, and the power here is 1. But now all that there is ready for the x cubed minus 4x squared plus 5x plus 1 to fill in. Okay, and now I am going to multiply, and here it comes the derivative of the inside function. So now let's go ahead and take the derivative here, or the derivative of g right here, g prime. So now I'm looking at 3x squared minus 8x plus 5. Okay, and we don't need to FOIL out to verify anything, but this is our final successful derivative of something like this.